AP Calculus students. Welcome to section 7.1a, area between two functions. So you already know how to find the area between a function and the x-axis between different axes, right? Boundaries, right? So what happens when we want to find the area between two functions? Well, it's just the subtraction of those areas, obviously. So let's take a look. Why do we study this? Because we know that area underneath a rate function between the x-axis gives us accumulation of whatever material that or distance that we're talking about. And so what happens if you have competing rates, right? Cars racing against each other. You have some water coming into a tank, water coming out. What is the total accumulation? And it would be the area between those two functions. And also, we actually produce, and again, a real engineering sense, real physical objects that have surface areas that may require two functions to write them. And we need to know exactly what that surface area is and exactly what its shape is. So notice if I asked you to find the area between A and B, between g of x and the x-axis, it would be, right, these marks here, right, these slashes here. If I asked you to find the area between this function f of x and the x-axis between A and B, it would be all these dots. So then if I asked you for the area between f of x and g of x, if you take the larger area and subtract the smaller area, upper function minus lower function, you get the area in between, right? So it really does matter when you do your integration that you have the upper function minus the lower function, because that's actually the area, right? So the integral then of the area between two functions would be f of x minus g of x, where f of x is the upper area and g of x is the lower area. Now, today we'll have basic problems. What else could happen? What could happen is that there are intersection points between the two functions and you have to find them instead of them being given to you. You may have cases where the functions switch, which one is upper and which one is lower. So you'd have to do two different integrals to switch the upper and lower functions, right? And so it could be that that the easiest way to write the graph that we see is using y's, and then instead of upper and lower, right, we would have right minus left, because the values on the right are higher than on the left. So that's when we wander into 7.1b and 7.1c. So let's talk about actual physical graphing. I just want you to know, like here on example 20, we're going to sketch the region between negative x cubed plus 3 and the y equals x line. And I just want you to know, like, if you took real graph paper and carefully graphed negative x cubed plus 3 and the y equals x line between x's of negative 1 and 1, with centimeter squared or inch squared graphing paper, if you counted up the squares in between these two functions, it would actually equal the area that we're going to find using integration. So it really does physically work. I also want you to know, so your calculator does a good job either on the math screen of doing integration for you, as long as you've set it up properly. It also does integration on your graphing screen, right? When you graph the function, you can choose second calc and it allows you to pick an integral. Your calculator cannot find the area between two functions straight out. Isn't that interesting? It can only find the area between a function and the x-axis. So what do we do to get around that? We put our upper function on a y1. We put our lower function on a y2. And on a y3, we write y1 minus y2. So we just have that one function that actually is made up of the subtraction that we want, right? To graph it, we turn off the equal signs, right? We de-highlight the equal signs on y1, y2, and keep the equal sign highlighted on y3. And when we graph it, we can then use our calculator, second calc, and pick the integration. And I'll try to show that to you here on my calculator. So let's take a look. Example number 20, it says sketch the region and find the area between these two functions here. Okay, so we're going in between -1 and 1. So let's go ahead and start sketching. Let's do -x cubed plus 3 first. I'm just going to pick an x to be -1, 0, and 1, kind of to help myself out, see what's going on. When I put a -1 into the function, right, this is -1 cubed is -1. Now it's a +1, and I get a 4 out. When I put a 0 in, I get a 3 out. And when I put a 1 in, I get a 2 out. There we go. It is cubic, so maybe it looks something like that. Hopefully I did a good job of drawing that. But that it's okay. It's just a sketch, right? The y equals x line, right? At -1, obviously x is, y is also -1 at 0, 0, and at 1, 1, right? And so we have this picture here. There we go. So let's connect, right? We're making the area where x equals 1 and x equals -1, and we have sketched the region. Notice that my upper function is -x cubed plus 3. My lower function is the y equals x line. So here we go. Let's integrate to find that area. I'm going from a lower x of -1 to an upper x of 1. My upper function, very important, is whoops, that's not horizontal. There you go. A -x cubed plus 3 minus, and I will subtract the x function. Please note, if your second function that you're subtracting has more than one term, you have to subtract all the terms, right? Well, let's integrate this, right? So that's -x to the 4th over 4 plus 3x minus x squared over 2. Let me check that out because I was just thinking of something again. I added 1 to the exponent divided by the new exponent, 3x. Okay, I think I'm okay. And that's from -1 to 1. So we're going to do our f of b minus our f of a. So what you're going to find is not many difficult substitutions here or anything. They're not trying to kind of break you on the integrals. Just, do you know how to set this up right? You'll see a lot of polynomials in this section. So f of b, I'm going to put the 1 in. That would be a 1/4 plus 3 minus 1/2. When I put in my 1 here, here, and here, minus f of a is putting in a -1. Let's see, that would be a 1/4. Now it's a -1/4 minus 3. Let's see, that would be a 1/2. It's still minus 1/2. Okay, so what I do here then is I do distribute my negative here, 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 and here. And then I just kind of look across and gather my like terms here, right? So here's what I see. I see, oh, did I forget? Sorry, when I put in a 1, let's go back. Let's check my work, shall we? Okay, here, let's go back. I'm going to check my work again. We're erasing. It's the little things, you know. F of b. When I put in a 1, right? That's a 1/4. Now it's a -1/4. I think that was my mistake. Okay. When I put in a 1, I have a plus 3. When I put in a 1, I have a minus 1/2. I think I did it okay now. Minus f of a. Okay. That will be a 1/4 because it's to the 4th. Now it's a negative. Here we go. 3 times a -1 is -3. And let's see, this is going to be a 1/2 because it's squared, and now it's a minus 1/2. There we go. Let me try that again. I always distribute my negative, right? And then I collect my like terms. I look all the way across. I don't try to just do the math here and here. I collect my like terms. Notice I have a minus 1/4 plus 1/4. Notice I have a plus 3 and a plus 3. and that is 6. Notice I have a minus 1/2 and a plus 1/2, and my area is 6. Literally, if you drew this region on graph paper, you would find you have 6 squares that are filled in, okay? I'm gonna throw this on the calculator too, just to show you. I'll try to make sure you can see this well. And I'm gonna put a negative x cubed plus 3. And then an x into my calculator. I always put the upper function on a y1 and the lower function on a y2. Right, if I switch it around, then it kind of messes me up. Right, consistency is key. So notice, let's see if you can see that where's the sweet spot there? Oh, there it is. I put that into my calculator. Okay. Now the next thing I'm going to do, there we go, is on a Y3, I'm going to use my variable button, which is by the cursor keys, variables, right? I'm just not doing well today here with this. Oh, there we go. Y variables in function. There we go. And I am going to put in Y1 into my Y3, Y1. So I'm on a Y3, I hit variables, Y variables in function, and I'm putting in Y1 minus Y2. Variables, Y variables function, picking Y2. There we go. So again, you think I could get this right. Okay, there we go. All right, now I'm going to de-highlight the equal sign on Y1, Y2 so it doesn't graph it and it only graphs Y3. There you go. If you see that, there we go. De-highlighted. Okay, zoom 6. You should be laughing at me by now, seriously. Like I'm just trying to get the calculator screen in the zoom. It's silly. There we go. So it looks like this. There we go. Where's my graph? Really, seriously, who am I right now? Okay, gosh darn this light. There we go. Okay, looks like that. Okay, so now I'm going to do second calc and pick the integral. And my x's are in between -1 and 1, lower limit and upper limit. And it does, in fact, then show me the area, and it does show that the area is 6. I'm having a rough time, but I refuse to stop the video and do a new one. Okay, let's go over. Of course, we have to have trig, right? We always need help with trig. So let me see if I can adjust. My curtains kind of have this bright, shiny spot. I think we'll be okay. I'll check and make sure that you can see it. What if you're asked for the same thing? To find the area between the regions when f of x is sine of x and g of x is cosine of 2x, in between -pi/2 and pi/6, and they ask you to sketch the region. Okay, let's do sine of x first. So sine of a -pi/2, right, is a -1. Sine of 0 is 0. And sine of pi/6, right, is 1/2. There we go. Right, so we know it looks like this. There we go. There's sine. Cosine of a double angle, let's start with a -pi/2. When I put in a -pi/2, I have the 2's cancel, and I have cosine of a -pi, which is -1. Not surprising that they touch there. When I have cosine of 0, when I put a 0 in, cosine of 0 is 1, right? And then cosine of 2 times pi/6 is cosine of pi/3, right? And of course that is 1/2. So they are connecting right here. There we go. So here's my region, right? So you just get appropriate points to help yourself out. Notice that cosine of 2x is the upper function and sine of x is the lower function. That matters. Let's set up our integral. We are going to integrate from -pi/2 to pi/6, and we are going to go cosine of 2x minus sine of x. Again, if my second function that I was subtracting happened to have a two terms, I would be sure to subtract both of them. Okay, I'm gonna come on down here where it's not so bright, right? And I'm gonna go ahead and integrate, and I think I can do this without a substitution because it's only cosine of 2x that I have. So first of all, I believe the integration of cosine of anything is sine of anything. So sine of 2x. I believe that my two choices in dealing with this too by the chain rule is to multiply by 2 or divide by 2. So you can't really go wrong by checking it. I believe that the integration of cosine of 2x is sine of 2x over 2. Let's just check. If I took the derivative here, sine of 2x, the derivative would be cosine of 2x times the derivative of the inside function, which would be 2, and they would cancel. Okay, so integration usually has the division of that that constant to overcome if you do the derivative, the multiplication by the chain rule minus. Okay, so I believe that the integration of sine is of a negative cosine. Negative sign would be a positive cosine. So again, let me just check. What is the derivative of cosine? That would be a negative sign. And so I'm right. Let's evaluate that from negative pi over 2 to pi over 6, right? Here's my f of b, right? So when I put pi over 6 in, that would be sine of pi over 3, right? Got that right here. Sine of pi over 3 is the square root of 3 over 2. Divided by 2 is the square root of 3 over 4. So plus, and then cosine of pi over 6 is the same, right? The square root of 3 over 2. Okay, let's just check that again. Let's make sure you understand what happened here. I put in pi over 6. 2 times pi over 6 is pi over 3. Sine of pi over 3 is the square root of 3 over 2. Divided by 2 is the square root of 3 over 4. Plus, still on my f of b, right? Let's see, cosine of pi over 6 is the square root of 3 over 2. Let's do our f of a minus. When I put in a negative pi over 2 here, I have sine of a negative pi, which is 0. When I put in a negative pi over 2 here for cosine, it's also 0. There we go. So our f of a was 0. So we need a common denominator. I'm going to multiply the second fraction top and bottom by 2, right? So notice this is still the square root of 3 over 2 here, but now I can add them. I have 1 square root of 3 over 4 and 2 square roots of 3 over 4. And my final answer for the area is 3 square roots of 3 over 4. Again, you could put this in the graphing calculator. Cosine of 2x, y1, sine of x, y2. On a y3, put y1 minus y2. You now have a new function, y3. You can ask your calculator to integrate that. So have a great day. Thanks for putting up with this, man, today, right? Have a good day.